approach limits when we're not looking at a picture, but just a function, is you're like, I'm going to try to plug in the 3, and if it works, I feel like, yay, I'm done with my limit. If it doesn't, then I probably have something else to do. Is this kind of how we think about things? I don't know, like what, so like what, yeah, so the top one, it's like as x gets really, really close to 3, what does this function get close to?
4 over 3.
4 over 3. And so it's not us saying like, well, at 3, this function equals 4/3. That's also true, but this is us saying as x got close to 3, the values here got close to 4/3. What happens if you try to plug in 3 to this one?
Undefined.
Yeah, and in fact, what kind of form do you get?
0. Probably like.
Yeah, so this is like 0 over 0, and we might say this is indeterminate. Have we heard this word before? Indeterminate. So what this is saying is that like, just kind of trying to plug in the 3 wasn't enough for us to come up with the actual answer. Okay, so yeah, I think this one is like screaming to be factored, right? How would you factor the top?
Yeah.
X minus 3, and then what could you do? That's right, you cancel these out. And then what happens as x is approaching 3? Yeah, this is actually approaching 6. So limits are these things where we have to be careful. We're not talking about evaluating functions. Sometimes they work, like when the function is continuous. But sometimes, if the function is not continuous at this point, we can still get a finite value because limits are not about what's happening at that number, but what's happening close to that number. So I think, I know someone was saying like, x approaches the number. So let's just say the general idea here is what happens close to a number, but not necessarily at the number. Right? This would be kind of a summary of what we're saying by limits. We're saying, like, kind of zoom in and what's happening close to that, but not actually at the number. Anything else anyone wants to add about the idea of a limit? Or so yeah, so discontinuity. So I guess continuous has to do with limits. Like if the limit as x goes to some number of a function is actually the same thing as the function at that, this would be continuous. F is continuous. But discontinuity is like kind of what we're saying here. Is this function continuous at 3? No, because you can't even plug 3 in there. So you're right, that limits are how we sometimes determine if a function is continuous or not. We think about it in terms of a limit. And maybe I'll throw one more idea up here, and we'll do this maybe tomorrow or the next day. Do I always have to have a number here?
No.
What other symbol could I throw up with this? Infinity, good. So a really important idea that's going to come up a lot in Calc 3, or sorry, Calc 2, is limits, let's say limits at infinity. And we already saw this idea on one of the graphs earlier, right, where we took a limit and that was telling us about a constant. Okay, limits at infinity. And again, we'll come back to it. Integrals. What do we think about for integrals? Okay, so this is like the opposite of the derivative, and in fact, we compute a lot of integrals by finding antiderivatives, right? That the integral of some function is actually the antiderivative. And what kind of integral is it when I don't have any numbers in it? Do you remember what that's called? There's kind of two types of integrals that show up, right? There's ones without numbers and ones with numbers.
Oh yeah, 1, 2.
So yeah, so these are the bounds for the integral, but I guess usually we would call this a a definite integral.
Oh,
Does that sound familiar? And then what's the one called without bounds? Indefinite. You're exactly right that that a and that b, we call them the bounds of the integral. And what's the difference between these? Yeah, like I have the bounds, so what do I do with the bounds when I'm integrating? I plug them in, and which order do I do things in?
Subtract b.
Yeah, I do f of b minus f of a, right? This is the fundamental theorem of calculus. So whatever you do here, this is a number. Right? Like I get a real number out, like 5 or 1/2. Here, so right, I'm using capital F to denote an antiderivative of little f. Or in other words, if I take the derivative of capital F, I just get back to little f. Okay. The indefinite integrals, do I just spit out the function, or is there another thing I'm missing? The constant. Does this sound familiar? This like, don't forget the plus c. Yeah. So the plus c is important because this is saying not just like find one antiderivative, but find all the antiderivatives. And so the plus a number is saying, well, I could add any other number I want, and it would still be an antiderivative because as Valerie pointed out to us, when I do the derivative of a number, what do I get? I just get z. So when I do the derivative of this, I will just get back to little f, because the derivative of c will just be. When I'm doing like a definite integral, and I get this number out, what does this number represent in terms of the graph of f? Ooh, so yeah, so you're thinking about something between the curve and the x-axis. What is it? So slope is about derivatives. What do integrals measure? When I tell you, you guys are going to remember. Maybe area under the curve? Does this sound, is this like, oh yeah. So if I had some function f from a to b, and I like shade in this region, right? The area of this shaded region would come from taking the integral from a to b of my function. Okay. Are there any, I don't know, anything else that we remember about integrals, or is this kind of mostly?
I remember the whole rule, but I.
Yeah, okay, rules, this is a good one. So that we had a power rule for derivatives. Do we also have a power rule for integrals?
Yeah.
We do, yeah. So power rule. So if I'm doing the integral of x to the n, how does it work this time?
It's going to be x plus 1 over n plus 1.
Good. Does this work for all n's? Or is there like one sneaky n that we can't use? Like what n would be bad to have -1? So this is all good as long as x is not negative. Sorry, n is not -1, right? Because I can't have that.
Yeah.
So that's actually a special piece. But in general, the reason I'm bringing up these power rule is that I think probably when you guys you've done a bunch of power rule problems, you're like, sure, power rule is like the easiest rule. Yay, thank goodness. In Calc 2, you have so many problems where you're doing derivatives and antiderivatives that your brain is going to start mixing up the power rule. So, you can make up whatever mnemonic you want, or maybe you don't mix up the power rule. Congrats to you. But for those of us who mix up the power rule a lot, something that I think about for derivatives is that I'm decreasing the power, and for integrals, I'm increasing the power. That could be something that helps you remember. But I've seen this a bunch of times that you're like a super pro at the power rule, and then when you have a problem that makes you do the power rule both ways, you're like, which one is it? So that's like a heads up warning about stuff in Calc 2. Okay. Do we have questions about these ideas right now? Okay, so here's what I have for us, and you can just kind of spend a little bit of time on it now before heading to lunch. I wanted to give you a chance to accumulate like a collection of derivatives and antiderivatives that show up all the time so that you can get like really fast at working with them. So I have here just a list of kind of what I think are some of the most common types of functions that you're going to need to differentiate and integrate. So just kind of, fill in all the ones that you feel like you can fill in real fast, and then if you have questions about, I don't remember how that one works, let me know. still be thinking, but if you wanted to start comparing some answers with neighbors, like maybe there's a couple you couldn't remember, but your partner could remember.
That makes it good. Yeah, those are more.
Would we like to check our answers as a class?
Yes.
Alright, so I think maybe this first one's very similar to the one that Valerie suggested earlier. Can someone tell us how this one works? Yeah, so we've got, I hear 5x to the fourth minus
12x squared.
12x squared, because we bring that 3 down and multiply to the 4. And then is there anything else? No, plus 0, because whatever. Okay, so power rule is not so bad. What's another one that you felt like really good about?
Second one.
The second one. How did you treat this one?
For that one, I chose to rewrite it so I could see the exponents instead of just the squares.
Great. So you were like, hey, secretly, these are power functions, right? So what's that? So square root of x is x to the 1/2. What happens when the square root's on the bottom?
Negative 100.
Right, x to the negative 1/2. So then this would be what? 1/2 x to the negative 1/2. Yeah, so it's like plus or negative, so this could be minus 1/2. Yeah, to the negative 3 over 2 because we're subtracting 1 from the 1/2. Any questions about that one?
Did we simplify it or did we not?
Yeah, so this is great, but you're right. Maybe you are wanting to recognize some properties about this and you'd like to write it without the negative exponents. So what would happen with like the first x to the 1/2? How would you rewrite it?
1/2
Yeah, 1/2 square root of x minus 1/. And this one you can write multiple ways, right? You can write like 2x to the 3/2, or you could write like square root of x cubed. And that would be fine too. Okay. What other ones do we know? Like sine and cosine, they're kind of like buddies.
Yeah.
How do their derivatives work?
Make them both.
So we've got.
Sine is cosine.
So I think, do we feel like pretty much good that this one's going to turn into a cosine and this one's going to turn into a sine, but the part that we often mix up is which one has a negative? Okay, so the cosine, derivative of cosine gives us negative sine x, and the derivative of sine gives us positive cosine x. Does anyone have like a way that they like to remember this, that they'd like to share, or that they just memorized it?
Yeah.
Okay, so that's fair. You guys just memorized it. If you get really, so like something that is going to be useful in this class is being really, really like fluent and comfortable with trig functions. And so in fact, like one way that you could think about this, maybe this is useful and maybe this is not, but like cosine starts up at the top and then it goes down, right? Something like this. and sine goes right through the origin, because sine of 0 is 0. And we know that the derivative is the slope of the tangent line. So, in fact, for cosine, when we're kind of like picking points and looking at tangent lines, the slope is negative. And that's why this is a negative sign. Whereas for sine, what's the slope here? It's actually positive. And so that's giving us a positive cosine. That's one way to think about it. But if you're like, oh, that's a lot because of the graphs, whatever. Come up with your own way of memorizing it. That's fine. Okay. What other ones on here do we think like we know? What about e to the x? It's just e to the x. Thanks, Karen. So yeah, e to the x, this is the one special function that just kind of stays the same. But what happens if we stick another number up in that exponent?
Yeah, for the power.
Just bring down the 5.
Yeah, so, okay, so what are we really doing? We've got a 5x plugged into the e. Yeah, because what rule do we need to use?
No.
So this is really tricky. I know this is this thing where we're like, it gets very confusing between like, I've got this power in here of 5. It's actually not that I have a power function. A power function is x to a number.
Yeah.
But this is a composition, right? This is e with 5x plugged in. So secretly here, we'd be using the chain rule.
There we go.
Yeah, I know. It's like what's it called? Chain rule. This is the rule that we use when we got stuff plugged in. So how does that work? We take the derivative of the outside thing, which is e, and so it just stays e to the 5x, but then what do we have to multiply by?
By the
Yeah. So we multiply by the 5, and it doesn't matter. A lot of times people will stick it in front because that just looks nicer. The reason I put this one in here is that, like, cool, we use the chain rule, it comes up a bunch. You will see this function, e to powers of x, lots and lots of times in Calc 2, and it will be nice for you to just start getting fast and saying like, well, I know that it's just 5 e to the 5x. So what's the derivative of e to the 3x? 3e to the 3x. What's the derivative of e to the negative 2x? Negative 2 e to the negative 2x. So this is one that you can like add to your I'm fast at it repertoire, and that will be useful. Any questions about that one? Okay, what about natural log? 1 over x, excellent. So now maybe we could see when we go to the antiderivatives that that's the like special 1 over x case. It goes backwards. What about if we were doing the derivative of 1 over x? It's just the power rule. Good, it's just the power rule. Don't forget this. I see a billion of these every semester. The integral of 1 over x, or sorry, the derivative of 1 over x is natural log. No. It's a power rule. So how would you rewrite this, Pedro, as a power?
Well, I would have just put x to the negative 1.
That's right. And so then your derivative would be?
Negative x to the power negative
Exactly right. And then if you wanted to rewrite it, you could. You don't need to, but negative 1 over x. So please keep this one in mind. It is just a power rule problem. Okay, so now I've got like some special ones left over. These are just like ones that we maybe memorize. Does anyone want to suggest one of them? Tangent is secant squared. That is totally correct. You can like prove this using the quotient rule or something if you want, but you should just have it memorized because that'll make your lives easier. What about secant? Secant tangent. Alright, that one is secant tangent. There's also similar ones for cosecant and cotangent. They're like almost the same as these. You could memorize those ones too, it might be useful, but these ones will show up kind of the most. And then arctan. What even is arctan? Okay, so it's great. So it's 1 over 1 plus x squared, or you might see it 1 over x squared plus 1. Doesn't matter which way you write it. It is the inverse tangent function. So This is something where you've probably seen this before, where you have like arc functions, or sometimes they write it to the -1. But a lot of times you'll write arc so that you're not thinking that it's a -1 power. But it's the inverse of tangent. And really, this is just a memorized one. The derivative of this guy is 1/1 plus x squared, and that will show up. Okay. So how about, instead of getting into all integral stuff now, we will do integrals after lunch. So, so lunch, I don't know if they told you guys, I guess lunch every day is like 12 to 1. So we're just going early because you guys didn't take a break, because you're awesome. And then we'll meet back in this room at 1 p.m. and we will talk more integrals.
How do you pause this stuff?
I wanted to know, I heard that
Yeah, I'm going back to the math. You would like
You're
to
gonna borrow that
participate in
for,
that? Yes, absolutely.
free time?
Yes.
How do you pause it?
I'll pause it right now.
Like, so what I'm not sure is when we get started up in the fall, maybe what I can do is I can get your name added to the email list for Math Club. And I can tell you right now that most of our events are Wednesday afternoons. So
I should be on.
Is it a little stop button?
What do you have
I
class?
have a clock from, I believe, go back to
Why you gotta be such an idiot?
Oh, okay, perfect. Math Club is like 2:30 to 4.
Okay, it should.
It is, yeah, usually all the events are somewhere starting right around,
Is it?
yeah, right around 2:30 or 3, that's when they start. And depending on what they are too, it's like totally okay for you to come to an event that starts at 3 and then like slip out to regular class.
Okay.